Hello, my name is Javier and welcome to Rock Video Tutorials. This tutorial is gonna show you how to build and use an existing rock component. For this, we are gonna use the orientation estimator component that is under SLAM package set. So first thing is we go where we have our rock installation. In my case, it's under CuSLAM dev. We source our environmental variables, source env.sh. The orientation estimator component is under SLAM, so we go to where SLAM it is, SLAM origin. So here is our orientation estimator. If we go inside, we will see a manifest file that has a description about the orientation estimator. It's a collection of tasks that compute the attitude or the orientation of a rigid body using different techniques. Currently, the orientation estimator depends on some libraries, for example, the logger, the rock logger, the quaternion direct Kalman filter, an unscented Kalman filter as well for quaternions, and the aggregator. If we see the .origin file, we'll see some tasks we are interested in the indirect Kalman filter estimator. So this task has 3 input ports. One is a type rigid body state that gives us the initial orientation in quaternions. If any information is provided in this input port, it will assume a zero heading and a zero pitch and roll with respect to the north geographic frame. After that, we have an input port with data type IMU sensor giving us information of the heading of the vehicle coming from the fiber optic gyro. And the third port is IMU sample, so our accelerometers, gyroscopes, information, and magnetometers from this IMU. In our case, is a Xsense IMU. We are not gonna use the magnetometers in our case because we have a fiber optic gyro for the heading estimation. For example, how can we do this externally? We have some properties and location. One of those are use magnetometer as a Boolean flag that we can set false or true in order to merge or to consider the magnetometers in the indirect Kalman filter. Also, there are some location properties and sensor properties like sensor noise. The advantage to you as an indirect Kalman filter is fast response, and the inertial navigation equations are independent of the filter itself. For these properties or sensor values, we can put initial values here in the origin file, but after that also we can load using a config file, a YAM file. In our case, we have in a folder config and a YAM file with all the information that we want to set as for our task. If we want to have different values that we have in the .origin file. So now we are ready to compile the component. We type a make. Now it's compiling the orientation estimator. this make or out approach build dot will compile our component and also all dependencies that these components has that and needs to be specified in the manifest file. So now he is installing the component, and here we go, it's ready to be used. So in order to launch the component, we have a Ruby script. I have in a folder scripts video tutorials. So here I have the Ruby script and two logs. One is the DSP3000, that is the FOG gyroscopes, and the Xsense IMU log. These are logs both coming directly from the driver origin component that the driver gives to us. We can have a look inside of the Ruby script. So the Ruby script is launch the indirect command filter, logs all the ports. We load our configuration information file that is located in the config file. We call the task. We load the values that are as defined as default in the configuration YUM file. We open the logs, specifies in arguments of the Ruby script, and now we are connecting the input port of our task with the log streams. For example, here we connect the initial the IMView data to the IMView samples input port of the component, the FOG stream in the log to the FOG samples, and the initial orientation that in this case the Xsense is providing to with us with the initial magnetometers. We connect it to the initial IMView orientation. After that, we configure the task and we start. We are able to start. So now, for example, we can run. So for this, we type Ruby processlog.rb and the folder where the logs are located. It will start to build the index files. It can take a while. That depends how big is the log file. So here it's building, and here is our log control windows that we can see here, the Xsense IMView log and the FOG DSP3000. So now we just have to click on play to log. Here we see the initial attitude value in the quaternion and pitch, roll, and yaw. We can click again. We can go faster. Clicking here, we will see here the speed number. We can go slower. We can stop it. One thing that we could do also is to open another window, another console, source our environmental variables always. We can type rock display, and we will see a list of all the tasks that are running currently in our rock system. For example, now we have only one, the indirect command filter orientation estimator, that is here, and we will see the properties, different values that we load from the YAM file, the input port, the 3 input ports, the output ports. In our case, we have a attitude. So for example, we can have different views. One view will be the struct view. We can visually see the values of our orientation in quaternions. Since quaternions is not really an easy way for us to see the attitude of our rigid body, we can here also with clicking, right click, rigid body state visualization, and also an orientation view. In the typical heading compacts output and a virtual horizon visualization. for example, we can play it and we will see how the heading and the pitch and roll are changing. We can speed it up to be faster. We will see here how it is starting to change. We could also visualize in a plot, clicking on the right click button of our mouse, plot 2D. So in plot 2D we have the yaw, the pitch and roll in quaternions. In the x-axis we will have the time, and in the y the orientation output of these three angles in degrees. For example, here we can see how it's changing the roll, the pitch and roll, and the heading, the yaw, in red. We can also speed it up and go a little bit faster. We don't need to replay the whole log file if it's big. So for example, we can say we only want to play until here, more or less in the middle, and we can speed it up to go faster. Here in all the moments we have information. Clicking on the right side in the dance inspector of the rock display tool, the strict view of our quaternions and information. And here stop in the mark what we set. We can here closed the log, and here what we will see is we have a new log file. What is the orientation estimation log file? This is the output of our component, the indirect Kalman filter orientation estimator component. What we can do now, when we already create the log file, we can call rock replay in order to replay the log file. So we are gonna choose our log file that we just create, and we will have create the index. We will have the same log control with the number of different streams per output port, and we can again replay, stop. For example, we can also have an strict view again, strict view here with the current quaternion. We could also select plot 2D visualization, and why not an orientation view with the virtual horizon and compass, and click play it, and we will see how our output is changing. Again, we go faster. So we can click on the right button of our mouse and we can select auto scrolling, and now we can have a general view of how the orientation of our rigid body change over time, which is quite nice to analyze the output. So thank you for watching, and this is all for these video tutorials, and remember, visit our Rock Robotic website and enjoy rock and be part of the community.